Free fall. Since the beginning of time, objects have fallen, but it wasn't until the 16th and 17th centuries that scientists understood the physics and mathematics of falling objects. The Italian physicist Galilei, who was born in 1564 and died in 1642, is one of those credited with figuring out the laws of gravitational fall based on experiments. The English physicist Isaac Newton, born in 1643, hey, that was the year after Galileo died, to 1727, developed a broader theory of gravitation to explain Galileo's observations. Free-falling objects. Using experiments and theoretical analysis, physicists have confirmed this principle. Falling objects have constant acceleration. The principle assumes there's no air resistance or other complicating factors interfere with an object's fall. That is, the principle describes the behavior of free-falling objects. In this unit, assume that unless you are told otherwise, falling objects are falling freely. Okay, great. So here's this principle they were talking about. The broad principle of free-falling objects can be stated more precisely. The instantaneous speed of a free-falling object increases approximately 32 feet per second for each second of the object's fall. And this is, of course, on Earth. Other places, other planets have different gravities. And we're about to apply this a little bit. The simplest case of a free-falling object is when an object starts from rest, that is, when its speed is 0 at time 0. In this case, the object's instantaneous speed after 1 second is 32 feet per second. After 2 seconds, its instantaneous speed is 64 feet per second, and so on. Let's before we flip to the next page, let's think about this a little bit. Let's make a speed versus time graph. So what this is saying is if an object starts at rest, meaning its speed is 0, at time 0, it starts right there. And then let's do, I don't know, 5 seconds. 1, 2, 3, 4, 5 seconds. We'll probably run out of room. But we know that, if that's what its speed started out as, then after 1 second, the speed is going to be 32 feet per second. I'll write units right here, feet per second. So that means that after 1 second, this is what our speed is. And that's at exactly 1 second. So we're speeding up. Our speed is getting faster and faster, and it's a straight line. That's this idea of having a constant acceleration. At 2 seconds, it's just going to be 32 feet per second more. So that'd be what, 64? Let's draw a couple lines up here. 64, 96, 100 and something, 20, 128, and then 150. Okay, so that's at 1 second. At 2 seconds, it's going to be 32 feet per second more. So we're up to the 64. At 3 seconds, it's going to be 32 feet per second more. So now we're up to 96 feet per second. At 4 seconds, 5 seconds, and maybe you can see the pattern by now. But can you tell this is just a straight line? Straight lines represent constant speed. That looks pretty crooked, but it is straight. If I was a graphing machine, it would graph perfectly. But one thing that's really important to note is that our speed is changing constantly, but like the amount of distance I fell after 1 second, like if I was free falling, can you see that? Free falling, the distance I'd fall in 1 second would be way less than the distance I fell in 2 seconds, because at the end of 2 seconds, my speed is way faster than what it was at the end of 1 second. So even though the speed is linear, our distance fallen is going to be exponential, or really it's a parabolic or quadratic or whatever. But anyways, we're going to look at that. So that's it for this page. Let's move on to the next page. from acceleration to distance. Your task is to use the principles just stated to express the distance an object falls in terms of the amount of time it has been falling. Assume an object is dropped from rest and falls freely. How fast is the object going at 5 seconds? How far does the object fall in the first 5 seconds? Okay. So really, all the information is that we know that acceleration on Earth is 32 feet per second every second. Great. So let's start just by looking. We're going to draw that graph again. And let's start by looking just at 1 second. Remember, so after 1 second, our speed is going to be 32 feet per second. And the question is, well, how far did I fall in that 1 second? Well, in this one, what's true is our speed was changing, so it's actually hard to say exactly what our distance was. But we're in luck. Because it's changing constantly, we can actually determine an average speed over that interval. So to determine the average speed, what we'd have to do is we'd say, well, if we're taking the average of two speeds, right? The speed at 0 seconds and the speed at 1 second. Well, what's the speed at 0 seconds? It's 0. So let me label this. Average speed from 0 to whatever time we're looking at. I'm going to make a table. I love in-out tables. So let's see. I think let's skip 0 for now. But if we're looking, and this is our time, of course, in seconds. So after 1 second, our average speed is just going to be 0 feet per second plus 32 divided by how many speeds are we testing? Just 2. So our average speed is going to be 32 over 2, which ends up being 16 feet per second. Okay, so if our average, actually I might not use this table. I'm not going to use this table. If you made it, good job, but you can stop making it. We're going to make another table later. So then if our average speed over this 1 second interval was 16 seconds, then the next question we might ask is, well, if we took an average speed of 16 feet per second times 1 second on that interval, then that's going to tell us our distance we fell. So now our average speed was 16, and we fell for 1 second, so our distance that we went was 1 second. So let's actually make a little bit better of a table. So we've got our time. We could figure out, let's see, we could figure out speed, and then we could figure out distance. Okay. So what we just figured out, we know that at 1 second, our speed at the end of 1 second is just 32 seconds. And our distance that we fell is going to be, let's see, we just did 32 over 2, right? That was that, which got us our 16, times 1 second. And that's equal to 16 feet. That's how far we fell. Okay. Let's keep going. What about with 2 seconds? Well, at 2 seconds, and we talked about this a little bit already, so hopefully it's not too boring. But we're still going, right? So 2 seconds now. Well, now let's figure out what our speed is. It's 64, which is really just 32 times 2, right? And we already talked about that. Every second you just add another 32. So there we go, 64. Then let's talk about our distance. Well, what would our average speed be from 0 to 2 seconds? Well, that's just going to be 0 plus 64 divided by 2, and that gives us our average, which is now going to be 32. So now we just do 64 divided by 2, and that gives us 32, but I'm going to leave it like this so we can see the pattern. And what we're doing here is we're traveling now for 2 seconds. So now instead of multiplying our average speed by 1 second, we traveled this average speed for 2 seconds. So then we're going to multiply it by 2. And that'll give us 32 times 2, which is equal to 64 feet is the distance we traveled. 2 more. Oh, maybe 3 more. Okay, now our speed at 3 seconds. 3 seconds, which is going to be another 32. Well, I guess let's see. 32 times 3 is 96. Yep, so 96. And there's our line. Now we say, well, okay, great. What's our average speed? That's just going to be 96 plus 0 divided by 2. That's going to be somewhere in here. 96 plus 0, 96 over 2. I mean, each time it looks like we're just dividing our speed by 2, right, to find the average speed. And how many seconds did we travel this average speed? 3 seconds, of course, or 3 seconds. So then we say, great, what's 96 divided by 2 times 3? Let's see, 96 divided by 2 is 48. 48 times 3 is 150 minus 6 is 144 feet. All right, let's actually see if we can't find a little bit of a pattern. Now, instead of 1, 2, or 3 seconds, we're going to just solve for a general expression being t seconds. Actually, no, we should do this. Let's do 5 seconds first. We're going to skip 4 because I'm tired of crunching numbers. Let's think about it like this. Well, here we just said we found out that our average speed was 96 because it was just 32 times 3. So for 5 seconds, yeah, because we're skipping 4. For 5 seconds would just be 32 times those 5 seconds. And that's going to be, did we already figure that out on the last page? It was 150, right? I guess I can always just double check with the old calculator when I'm not sure. 32 times 5. Oh, 160. I'm glad we checked. So then that means we're going to take our average speed, which is 160 plus 0 divided by 2, right? Because we're starting at rest. That's why we do plus 0. And how many seconds did we travel that for? 5 seconds, the average speed, times 5 seconds. And that's going to equal, let's see, divide by 2 times 5, 400 feet. Wow, traveled 400 feet in the time of 5 seconds of free fall. That's actually a lot. Imagine like falling off of a mountain, like a rock face. Those things usually, I don't think 400 feet would be a pretty big rock face to fall off of, and you could fall for a whole 5 seconds. Anyways, that's kind of a dark thought. Now let's generalize it, because we just answered question number 1, right? How fast is the object going at 5 seconds? We just figured that out, 160 feet per second. And then how far does the object fall in the first 5 seconds is 400 feet. Next up, we're going to generalize our work from question 1 to develop a formula. All right, see ya. We're going to, from formula 1 to, all right, see you, Ryan. From formula 1 for how far the object falls in the first t seconds. So all we're going to do is we're going to try and see if we can make sense of this work to plug in a t for a number of seconds. Well, let's take a look at our speed first. Here we just have 32. Maybe not super helpful yet. But here we have 32 times 2 seconds, 32 times 3 seconds, 32 times 5 seconds. So it would make sense to just say it's 32 times however many seconds you have. And if your number of seconds is represented by the letter t, then our answer for this one is just 32t. For distance, what you can do is let's just see if we can find anything that's constant. Look at this. We're dividing by 2 every single time. So we know that whatever we have, we're going to divide by 2. Then, the other thing that's constant is that we're always multiplying by the number of seconds, which means at the end of this, we've got to multiply by t seconds. And now here's the part where it gets a little tricky, is our numerator is different every time, right? But we know that our numerator comes from our speed column, right? Like the number, our speed that we're going is, that's the number we're dividing by 2. So if we can take our general speed and plug it in right here, 32t, we're good, right? Because that's how we found that number every time. Now this is a little bit messy, but I want us to pause and just say, look at this. The gravity on Earth is 32 feet per second every second. So on Earth, we just have 32 times however many seconds you've fallen, divide by 2, times however many seconds you've fallen again, and that's going to get us our distance. You should remember that because the 32 is very important for Earth, but if you ever had a quiz, say, where you had to figure out something like this on the moon, you'd use the moon's gravity, the acceleration of gravity, instead of the Earth's. But let's simplify this one for now. So here we'd say, well, cool, 32t over 2 times t, we can simplify 32 divided by 2 is just 16, and t times t is t squared. So our equation for distance fallen, and we're going to use an h for like height, like the height you've fallen, is equal to 16t squared. Okay, and that is our answer for number 2. Generalize your question to how far the object falls in the first t seconds. H equals 16t squared. Suppose the object starts falling from a height of h feet. What is its height after t seconds? Oh, I shouldn't have used, let's use a d, sorry. They're using an h later. So that's your distance fallen. Suppose the object starts falling from a height of h feet after t seconds. Assume the object has not yet reached the ground. Well, in this case, maybe we're thinking of like something like somebody jumping out of an airplane. Hey, look, that's a pretty good airplane, right? And let's say the airplane is h feet off the ground, and the distance you've fallen is d. So then if you've fallen for, let's say, this many seconds, then you'd be at this height now, which is really just this total height minus this distance that you've fallen. So our answer for number 3 is going to be your height minus 16t squared. Kind of cool, right? Great. H equals, nope. Oh, I guess your height equals h minus 16t squared. Use your result from question 3 to find an expression in terms of h for the amount of time it would take for the object to reach the ground. Oh, we did that. Wait, right? Oh, okay, so now use your result from question 3 to find an expression in terms of h for the amount of time it would take for the object to reach the ground. So now we're solving for t. So in this case, we'd say, well, let's see, I'm going to label number 4 right there. We'd say if you fall from a height, wait, I want to say, suppose the object starts falling from a height of h feet. What is the height after t seconds, assuming you don't reach ground? Okay. Oh, from question 3. I don't know why I'm getting so confused. Oh, then we could just say, ready, from question 3, we could solve. I'm going to actually take a little detour here and kind of not answer this exactly as it's asked. We know that the distance you've fallen, or the height you've fallen, is equal to 16t squared. And so if you ever want to find out, well, what was your distance that you fell? You could always just solve this equation, or you could just plug in a time for that equation. But if you knew the distance you fell and you needed to know how long it would take you to fall that distance, then you would solve for your time. So we're going to do that. So we're going to divide both sides by 16. Then we get h over 16 equals t squared. And then to solve for t, we just need to take the square root of both sides. So then the square root of h over 16 is equal to your time that you've fallen. This is really important. Remember this. Here's your two really important ones. They're both in boxes. That's really important. That's really important. Okay. Number 5. Suppose the platform is fixed at 90 feet above the ground. The diver falls freely from rest, and the water level in the tub is 8 feet above the ground. How long will it take the diver to reach the water? So what we're looking for is, we'll even use how about a little diving board. Here's a diving board. We got a tub that's 8 feet from the ground. The total height right here that the diver's diving is 90 feet. And our question is, what's the fall time from here to the surface of the water? We'll call that F, fall time. Oh no, actually let's just call it T for time. What's the time it'll take for us to hit the water? Well, we can actually just plug it in right here. Because what's the distance that from the diving board to the surface of the water? Well, wouldn't that be, let's see, I'm going to write this, time equals the square root of h over 16. And let's plug in, what would our h be? Well, our height would be this 90 feet minus this 8 feet above the ground that the surface of the water's at, and then divide by 16. Once we do that, we get, of course, that the time is equal to 82 over 16, but of course the square root. Let's see what that would end up being. 82 divided by 16. Oops, I forgot to take the square root. Oh, bummer, it didn't work. Square root of 82 over 16. So it looks like it'll take 2.26 seconds. All right, and that's all our work for this one. Thanks for watching.